Whenever you've got math questions, you've got a math teacher here. Little AMA. Ask me anything. In the meantime, I am just graphing some triangles. And one of the things that I'm asking my students to do is find something called the circumcenter. So the circumcenter of a triangle is one of the measures of the center for a triangle. Because if you think about it, like a triangle there's a lot of different ways that you could kind of talk about like what the center of the triangle is, right? So it could be like the same distance from all the sides, or maybe it's the same distance from all the corners, or maybe it's like the balance point where that is, right? There's lots of different ways to talk about like the center of a triangle. So this is just one of those measures of center, which is called the circumcenter, which is, it's if you were to draw a circle around the ends of or not around the ends, but around the vertices of a triangle. So if I have a triangle like this. Actually, hold on, wait. It's actually easier for me to draw the circle first. Okay, so if I have a circle here like this, and then that's the center, right? That's an okay circle. So then if I have a triangle that's within this circle here, like this, and this, and that, right? So that center there, that center right there in that part is called the circumcenter. So what that means is that, well, I mean, by definition, that means that the distance from this center out to each of the vertices, I drew that terribly, out to each of the vertices, the vertex, the points of the triangle, those are all going to be the same distance because they're the radius of the circles, right? Or they're the radius of the circle. Okay, so those would all be the same distance. Now, what's really interesting about this is that when you look at this, this is also made by the perpendicular bisectors of all of these sides of the triangle. So like all three of these sides, if I divide these into perpendicular bisectors, like they're always going to be the perpendicular bisectors, right? And Charlie was definitely listening in class because, yep. So this triangle is all acute angles, so the circumcenter is in the middle or inside the triangle. If it's a right triangle, it's going to be on. It's actually going to be. You might be able to see this one. I don't know. This one is a right triangle, and so the circumcenter actually is on the vertex, or not the vertex, but the hypotenuse of the triangle. And then if it's an obtuse triangle, it's actually going to be outside of the triangle. So that's pretty cool stuff. There's just lots of different ways to look at these triangles and things like that. And so then you can use the information like these are all going to be the same length. And these perpendicular bisectors, they are dividing like these sides of the triangle into even like congruent sides or congruent pieces, right? So what grade is this? This is typically in a geometry class. So it sort of depends on if you're taking it in 10th grade or 9th grade or maybe 8th grade. It just kind of depends on the district. But we at my school do like an integrated math approach. So instead of doing like a pretty typical like traditional pathway is 9th grade is Algebra 1, 10th grade is geometry, 11th grade would be Algebra 2 trig. That's what we used to do, and what we've done now is we've taken those 3 years of math and we've condensed it into 2 years. So like in your 9th and 10th grade year, you basically get through all 3 of those years, like geometry, algebra 1 and algebra 2 trig, like all in one or in 2 years in a sequence of 2. So yeah, so this is mainly going to be high school. You might see this in some middle school geometry classes. You don't know. I don't know. Just depends. Yeah, so algebra 1, you may or may not see this. I don't know. Depends on your teacher, depends on your district, all of that kind of stuff. Yeah, GeoGebra is really fun, or GeoGebra? I don't know. That's a really cool method or thing to use when you're especially working with geometry and things like that. But for now, this is a worksheet with my honors students where I'm having them graph the triangles, and then they have to find the perpendicular bisectors of each side length, and then mark where the circumcenter would be. Ooh, rationalize the denominator. I can definitely rationalize the denominator. Okay, here's all of these. Okay. All right, so rationalizing the denominator. So this is a thing that you have to do typically in like, you probably get into it with like algebra 2, I would say, is when you first really look at it. But some teachers will introduce it as soon as you learn about radicals, right? So when you learn about radicals, a lot of times some teachers will bring in that rationalizing the denominator. And it's actually like an old rule because, okay, so I'm getting ahead of myself. So let's talk about what it is. So if I had something like 3 over square root of 2, okay? So we've got the numerator and we've got the denominator. So rationalizing the denominator means you're trying to make the denominator into a rational number, okay? So I actually don't have my students do this anymore because the reason you would need this to be a rational number in the past is when you were using a slide rule to like divide different things and big numbers and all that kind of stuff. And you couldn't do an irrational number like this on a slide rule. So that's why you were required to rationalize the denominator. But again, you can just put this into a calculator and you can get a value for it. So nowadays it's kind of like, there's a lot of teachers that still do it. So like, I'm still going to show it to you. But personally, I don't do it. And I know a lot of other high school math teachers are kind of moving away from it as far as just like requiring you to do it. That being said, a lot of times like it'll show up on the SAT where they do have it rationalized. So you need to recognize that it's the same thing. So to rationalize the denominator, so we need to change this root 2 into like an integer, right? We need to change it into an integer. And so what we're going to do is we can multiply anything by 1. Anytime, anywhere, it's still going to be itself, right? Anything times 1 is itself. So even though this is not an equation, I can still just multiply it by 1. Now I could multiply it by 1 over 1. I could multiply it by 4 over 4, 10 over 10, right? Anything I could, x over x, right? I could multiply it by any version of 1, but I'm going to make sure that I multiply it by a version of 1 that's going to help me out, that's going to get rid of this irrational number, okay? All right, so I teach Genya Scrunkley. I teach mainly high school, but I've also taught all the way like middle school, lower school, through like AP Bio and things like that. And you can absolutely ask a 7th grade question for a test tomorrow, Isabel. Pop it in the chat and I will get to it, okay? All right, so why don't you just square it? So I wish that you could just square it. I do teach some 9th grade. But if I just square it, it's not going to be the same number, right? If I had 3 and I said, oh, well, 3 squared, then it's 9. It's not going to really work, okay? But what I can always do, remember, I can always multiply by 1. It's going to be the same number, right? So if I multiply this by root 2 over root 2, okay? So this is a version of 1, right? Root 2 over root 2, it's the same, anything over itself is 1, right? But here's what the magic thing is. It's not magic, it's math. But it feels like magic sometimes, okay? So we've got 3 times root 2, so that's just going to be 3 times root 2 on top, right? Because remember, we multiply fractions straight across. That never changes. Now, root 2 times root 2. So the square root of 2 times the square root of 2. So let's think about this. I like to show this in as an example of like with familiar roots. So if you do like square root of 9 times square root of 9, okay? That is square root of 9 is 3. Square root of 9 is 3. So 3 times 3 is 9. So if I take a square root and I multiply it by another square root of the same number, right? It actually just kind of drops that radical. Okay, now the reason is because you're basically doing like square root of 2 squared, and that's going to just bring that 2 out. So this becomes root of 2 times root of 2. That becomes just 2. So now I no longer have that radical in the bottom. Now it is a rational number on the bottom, right? It's an integer on the bottom. So we have rationalized the denominator. There you go. Okay. All right. Do what we worked on in C block, please. What did we work on in C block, Stella? What did we work on in C block today? You weren't in C block today, Stella. So this grade level here, usually you're really working with it. You're really working on it is with like algebra 2 is when you're going to mainly be looking at it. Yeah, this would be the rationalized denominator. So again, algebra 2 is when we're mainly going to be looking at it, but you may see it in 9th grade. I know some 8th grade teachers, sometimes some teachers, as soon as you start doing square roots and radicals, they teach you this. Okay, because it's one of those things, a lot of times like teachers they won't accept this. It's sort of like a non-simplified or an unsimplified fraction. But again, other teachers are kind of moving away from that. Okay, so Isabel, so is it diameter? Is that what you were asking about? Is finding the diameter? So no, kinda. Getting the number for what? You gotta give me a little bit more information. Yeah, Stella, you're in D block. You're not in C block. Ooh, AP Calc BC. I'm so sorry. That is beyond. That's beyond me. So I can go up to about pre-calc, but beyond that, AP Calc, especially AP Calc BC, that's really tricky for me to do. So I can't be much help with that. Okay. If the square root was on top, you wouldn't have to do anything. This is only something that you have to do if the square root is on bottom. Okay, so Isabel, finding the circumference. Okay, so finding the circumference is something with circles, right? So with a circle, okay, trying to get the answer from circles, radius. Okay, so the circumference of a circle is just like, ooh, that is a good circle. So the circumference of a circle, hold on, I gotta go let the dog in. Hold on, he's gonna make noise. Come on, bud. You wanna say hi? Come here. This is Nemo. This is the dog. This is Nemo. Say hi, Nemo. go down there. Okay. So the distance from the center to the side is your radius, right? Distance from the center to the side is your radius. That is a little r. Okay. You guys know I don't play Fortnite. Oh, I know, I should, right? I should start playing Fortnite. It's just not really my bag. I'm an open world explorer gamer girl here. I like Red Dead Redemption. I like Zelda. Okay. So the distance from the side to the side through the center, that is your diameter. Okay, now your diameter is 2 times, oh, that D looks weird, is 2 times what your radius is. Okay. Circumference is the distance all the way around the circle. So it's kind of like the perimeter of a circle. Okay. Now, what's really interesting is that, like, back, thousands of years ago, they meaning like ancient Greeks, Romans, everybody that was playing around with math and things like that, they realized that the relationship between the diameter of the circle and the circumference of the circle ended up being about 3. Okay, so they saw that usually the circumference was about 3 times the diameter on any circle, anytime they had a circle. Okay, so the circumference, as they studied it more and more and more, they realized that actually not just is it always 3, it's always 3.1415, on and on and on and on and on. So now we call that pi. Okay, so the circumference is pi times the diameter. Okay, now since the diameter is 2 times the radius, you can also say that the circumference is 2 pi r, because 2 times r is just the diameter. Okay, so if you're given, hi Henry, if you're given like the radius, you can plug that in. If you're given the diameter, you can plug that in. Okay, you can do 2 times the radius and then you get the diameter, but that's how you get that. Now, if you get the circumference, now if you're in 7th grade, do you need, with 7th grade, are you using the pi button on your calculator, or are you using 3.14? That's the question for you, Isabel. Is if you're using it doesn't really make a huge difference. Okay, so you're using 3.14. So then if you say like, oh, the radius of this circle is 10 centimeters, and you need to find the circumference, right? Well, the circumference, let's see, if radius is 10 centimeters, the circumference is 2 pi r, right? So that's going to be 2 times 3.14 times the radius, which is 10. So then you would multiply through there, right? And so you'd have like 6.28 times 10, so 62.8. So your circumference would be 62.8 centimeters, because it's distance around, so it's just going to be centimeters. Okay. So then, Isabel, is that helpful? Is that about what it is, or what? How did I get what? So I just used the formula. So I used the circumference formula, okay, and then I plugged in, like, it gave me the 10 for the radius, right? So 2 times pi times the radius, so it's 2 times pi, which is 3.14, times the radius, which is 10. So then 2 times 3.14 is 6.28. And then times 10 is 62.8. Okay, so with circumference and with diameter and area and all of that, they're really just based on, that's okay, you're fine. Isabel, please, you are totally fine, okay? But does that make sense? Right? So you're just looking at the formula and you're putting in the numbers where the formula is, and then you can use your calculator, or you can multiply it by hand. I'm not sure if you're able to use a calculator for it or not, but it's really just using the formula. So if you have the formula with 2 pi r, okay, you might be able to just do that. Okay. All right, so we had piecewise functions. Okay. Okay. Ooh, piecewise functions. Piecewise functions are fun. So functions are, let me get my, and Anthony, I did see you, I just didn't say hi. I was being stealthy. Okay, let's see. All right, so piecewise functions. Derivatives, that's a little bit more into pre-calc. Or really, I mean, the directed line segments with ratios, is that for calc? I'm not really, calc is a little bit beyond what I focus on in this level, but let's see. Directed line segments with ratios. Can you, chars, can you give me, yeah, I can't do, I am not an AP Calc teacher, guys. I'm sorry. Okay, so scientific notation. I'll do piecewise functions in just a minute. Piecewise functions. And then, okay. Yeah, with the, so you can say two triangles are similar by angle. But, so we'll do piecewise functions in just a minute. I'll get to that. But so similar versus congruent. So similarity means that they're the same shape, but they're different sizes. Now the same shape means that you've got the same number of sides and the angles are all the same, right? But so with a triangle, right? With a triangle, if I've got two triangles that look like this, right? And I say that, excuse me, and I say that this is 50 degrees and this is 89 degrees. And I could say that this is 89 degrees and this is 50 degrees. Okay? You know that all triangles add up to 180, right? So 50 and 89, so then that would be 41 degrees for this one, right? And it would be 41 degrees for this one as well. So because you've got two of the angles, there's only one possible value for that third angle. And right here, you've got, again, the two angles. So there's only one possible value for that third angle. So for a triangle, you only need to know two of the angle measurements because you know what that third one is, okay? So you've got two of the angle measurements. So if these two angles are congruent to these two angles, they're similar. They're at least similar, right? They could be congruent, but I don't know anything about the side lengths. So I can't say that they are definitely congruent, but I can say that they're at least similar, right? Because they've got three sides, because they've got those three angles. So that would be like the angle of similarity, right? Now, if I had one of the side lengths, I could then also prove that they were similar or even congruent, right? If I had like angle side angle or angle side. Yeah, those are two ways that you can use for congruency. Okay. All right, so piecewise notation or piecewise functions. Okay, I'm going to have to look at the directed line segments with ratios. I may just not be familiar with how they're being called that, but I don't know. Segments with ratios is a construction unit. Okay. All right, but let's talk about piecewise functions. So piecewise functions, they're functions that are split up into pieces. Mathematicians are not known for really creative names for things, so they are functions split into pieces. That's a piecewise function, okay? So you've got, let's see, you've got, let's say if we've got, you know what, actually, I'm going to go from the function first, and then we can do, so a piecewise function could look something like this. It could be here, there, then it might go down like this, and then it'll go here, and then maybe it goes there. Okay. So this right here, this is a piecewise functions. Piecewise function. It passes the vertical line test, right? If you're not familiar with the vertical line test, it just means like if a vertical line only passes through it in one spot, then it is a function. Okay, that's the vertical line test. But what this is this is not just a straight line. This is not just a linear function. This is not an exponential function. This is not a parabola. This is not a quadratic, right? What this is you've got all these little sections, these little pieces of the function, right? So, for example, when x is a value between, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when x is between -9 and -3, right, in that spot, this here. So you could say that between -9, when the x value is between -9 and -3, it's going to follow the equation of y equals 4. So that's one of the pieces, okay? And then this next piece, when x is between -3 and 2, okay, it's going to follow the line of, let's see, well, there's a y-intercept of 0, so it's y equals, what's that slope? 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. So -7 over 5x, okay? So this section here would be this section here. This one here is this one here, okay? So it's a function that's broken up into pieces, okay? Now there are lots of other things that you can do, like with, oh, and then there's holes and there's asymptotes and all these other things, but generally that is what a piecewise function is. It's just a function, it's just a line or whatever it is, that's that relationship that's going to change over different intervals, okay? So it's almost like it needs to be like an interval-wise function or something like that, okay? But piecewise function is what you've got. Okay, let's see here. Okay, let me see. Let me search up these directed line segments with ratios. I'm just going to look at what those are because I am not. Uh-oh, I might have typed in the wrong password. It might take a minute. You've gotten a bit. Guys, it means nothing to me. I don't play Fortnite, but Victory Royale, yay? I don't know. At some point, I'm going to play Fortnite. With Billy and JT. Okay, again, you guys will have to tell me about this tomorrow, about what the victory rollout. Yay, it's a yay, yay. The victory royale, is that like a battle royale? Okay, so directed line segments. I'm so curious. Ratio. Oh, so fractional distance. This is just fractional distance. Got it. Okay. All right. So now we got this. Oh, logarithms. Oh. Type in ratio 3, 5. Okay. Ratio 3, 5. Yeah, so are you finding your... Let me see. The ratio is 3 to 5. Okay, so Chars, are you just doing line segments, or are these on a graph? Like, do you have to do like the slope and the distance and all of that? Or is it just like a line segment itself? There's a slight difference, but I mean, so ultimately this directed line segments with ratios, when I taught it, I always just talked about it as fractional distance, or you kind of talk about like how these different things, you find the line when you get, oh, you're constructing fractional distance. Oh, okay. Let me think. Okay. Constructions are really, really, really hard for me to show here, because I don't have like a good way to show it on the, but so I'll do my best to kind of explain it. So when you're dividing it up into, let me see if there's another, the way that I'm thinking about doing it. Okay. So here is what I'm thinking. Oh my God, this seems really, oh boy. Okay. This is not how I was planning on doing that. This is really hard for me to show. Okay, Chars. So here's the thing, is that the main thing to think about is that your compass, you're always going to use that to mark a series of points, or a bunch of points that are all the same distance from like the other point, right? So you've got your pencil side. I'm trying to show that. You've got your pencil side, and then you've got like your point side, right? So your compass is always going to be used to just show those points that are exactly that distance from your other point. Okay? So you've got the an array AX. Interesting. Okay. So basically what it's saying, I don't really know, but all right. So if you've got your original line segment here, right? And then what you're going to do, I think you're going to do this. So you're going to draw another line that makes an acute angle there. But it should be like the same. Okay. Okay, you know what? I'm going to talk to you how I would do this. I'm not sure, I don't know how picky your teacher is, if they want you to follow this directly, but here's what I would do. I would take my line segment, okay? So if you're dividing it up into a ratio of 3 to 5, the number of total sections you're going to have, remember there's a difference between a fraction and a ratio, right? A fraction of 3 over 5 would be I have 3 pieces out of 5 total. But a ratio of 3 to 5 means that I have 3 of one set, 5 of another set, so I have 8 total. So this line, if I'm supposed to divide it up into a ratio of 3 to 5, I need to have 8 total sections on here, okay? Now, it is really easy with a compass to divide a line in half, right? So you would do like a perpendicular bisector, right? Or finding the midpoint. So what you would do, again, this is really hard to show on this board, but so you would set it up so you would have your, we gotta make sort of a makeshift compass like this. Okay, so I've got my pencil here and I've got my marker here. Okay, so you would set your compass, like your compass pin, right? The point on one end of your, so you learned the perpendicular bisector, right? So you would do like a curve like there, and you would do another curve same distance there, right? And then you cut that in half. That's really hard to see, I'm sorry. Right, so you would do like, it would look like that, and like that, and then you would draw that in half, so there's your midpoint, right? Okay. Now, a half of a half is a fourth. So then I would divide this into a fourth, right? I would do the same thing, but just between these 2 points. So there you have your next half, right? And you would do it over here too, right? You would go like that. So now I've got it into fourths. Now, a half of a half of a half is an eighth. So now, got this, so there's that, that, and that. So now I have it divided up into 8 segments. Now, the other way, like with the parallel line, and you have to do the acute line and mark those 8 things. I'm not sure why you're doing that, but regardless. So now you would say like, okay, well, if this is my one endpoint and this is my other endpoint, and I've got it divided up into 8 sections, right? If I need it to be like, let's say this is A and this is B, and you need to put point D in a ratio of 3 to 5, right? So what I would do is I would go, okay, so 3 to 5, remember it's a total of 8 sections, which we just marked. So I would go 1, 2, 3. That is where point D is, because this is 3 eighths, this is 5 eighths. So that is a ratio of 3 to 5. Okay. Again, might not be the way that your teacher is asking you to do it. They might want you to do like there's another line segment, and then you mark that line segment, so then you're just moving. Like this is kind of a mess, but I mean, if they kind of go like whatever, as long as you're just using your compass to do that and a straight edge, then this should be acceptable, I hope. Yeah, with the other line, that does work, but that is going to be, that I really can't show because I don't have the right tools for that. Like constructions is one thing that's just really hard for me to show on these boards and things. But this, like, hopefully conceptually, does this make a little bit more sense as far as like how to divide that up in the ratio of like the 3 to 5. Okay, so you do, so yeah, I'm sorry I can't help you a little bit more with that, but watch lots and lots of videos and watch it, pause it, do it. Start, pause, do it. Start, pause, do it, okay? But just practice, and it'll work out. But just remember that compass is gonna be like what you're marking with the same distance. And watch lots of different videos, lots of different people doing that. Okay. All right. So somebody had asked about scientific notation. Took Algebra 1 in 7th grade. Woo! That's intense. It's a lot. All right, so scientific notation. Scientific notation is used for really, really big or really, really small numbers. And we use like the power of 10. The power of 10. We use that in how we're going to do these numbers, because multiplying by 10 or dividing by 10 is really just moving the decimal for place value, right? So like, I mean, 5 times 10, sort of the most basic, right? You do 5.0 times 10, right? So then I would just move the decimal over, right? 5 times 10 equals 50, so it's the same thing as just moving the decimal over, okay? Well, hi, Camilla. Welcome. Welcome to my live. All right, so, I didn't mean to do that. So 5 times 10 is 50. 5 times 100 is 500, right? And again, it's just like moving the decimal. Boop, boop, just moving it over, right? So we can use this again for really, really big numbers. Now, writing out like 100, 1,000, 10,000, that gets old because like I don't want to have to write all those zeros. Like I'm using this to try to avoid writing these really, really big numbers, right? So instead of writing 100, I would write like 10 squared, right? Or I could do 5 times 10 to the 4th, right? And that would mean that I move my decimal over 4 spaces, because that would be 4 zeros, right? So that's 1, 2, 3, 4. Sorry guys, I've been sick. Okay, but I can also go the other way, right? So if I did 5 times 0.1, that's going to move my decimal to the left 1 spot. So that's going to give me 0.5. 5 times 0.01 gives me 0.05. Okay? But again, instead of doing the like times 10, times 100, times 1,000, I'm going to use my exponents. But when I get to smaller numbers like 0.1, I'm going to use 10 to the negative 1. 0.01 is 10 to the negative 2. Okay, so doing that, that is just making it a smaller number, right? And this exponent is like how many decimals that you move. Did you know that there's a pattern if you square a number and then add up all of the digits? Square a number and then, or do you mean there's a lot of patterns that come up with, like when you look at like Fibonacci sequences and like the Pascal's triangle. Pascal's triangle is crazy how many patterns show up. We did Pascal's triangle a couple weeks ago, but we can get into it again. So scientific notation, basic overview right there, right? So that's the basic idea. So if you have something, so when we're writing in scientific notation, the first part of the number needs to be between 1 and like 9.9, right? So 1.2 times 10 to the 4th, okay? Oh, Nemo, shush, 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 shush. So 1.2 times, yeah, so Dua Lipa is better than you. That is, yeah, that's Pascal's triangle. I think that's Pascal's triangle. Maybe not. 14977,941. I think it is. Okay, anyway, 1.2 times 10 to the 4th, that means that you're going to take 1.2 times 10 to the 4th, which means you go 1, 2, 3, 4. That's where the new decimal location is, and you fill this in with 0. So it's 12,000. Okay? Now, 1.2 times 10 to the 4th is not that much shorter than writing 12,000, right? But if you get into something like 1.23 times 10 to the 17th, I'm not writing out 17 zeros, or 15 zeros in this case, right? So being able to work with these larger numbers like this are nice, because you can also then, if I need to multiply it by something, then I'm just multiplying all these different things together. Okay, so that's kind of scientific notation. If you need more details, I'm not sure who asked for that, but if you're still here and you need need something else with scientific notation, let me know. Put it in the comments. Okay, distance formula. Chars, distance formula on a coordinate plane like this, I'm assuming. Or do you mean like physics, like distance traveled or anything like that? I'm assuming distance formula. Okay. Did you know that the distance formula is just Pythagorean theorem? That's all it is. Pythagorean theorem is like I would say the most used and most useful formula ever. It's just Pythagorean theorem. Yep. Okay. You can use it. I mean, anytime there's a right angle, you should go Pythagorean theorem, done. Okay. I even tell my students, I was like, the distance formula to me, I get so lost in like, it's the double negatives and the positives and then x2, x1, all of this kind of stuff. But when I just think of it as, oh, it's just the Pythagorean theorem, just kind of shortcut a little bit, then I'm okay. I feel okay about it. Okay, let me get my other coordinate plane because it's a little bit bigger. There we go. Okay, I like the squares on this one because they're a little bit easier to see. Okay, so if I've got 2 points, I don't know, let's say -1, 3, and we'll say 4, 2. Okay. All right. So we have -1 and 3. Lions touchdown. Woo-woo! All right. So -1, 3, and we have 4, 2. Great. So we've got these two. Where did I put my ruler? Oh, that's right here. Okay. Okay. So I'm going to find my distance between those two, right? Now, my distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. The only reason I know that right off the top of my head like that is because I just went over it with my students today. Because otherwise, I see this and I go, Pythagorean theorem. Because if it's on a coordinate plane, or even if it's not, you can still figure it out. It's just a right triangle. And you're finding the hypotenuse. That's all it is. Right? So this is 1. And this is 1, 2, 3, 4, 5. This is 5. So Pythagorean theorem is a squared plus b squared equals c squared. So we'll just call this side c. Okay? So I know that 1 squared plus 5 squared equals c squared. And we'll get to the distance formula in just a second, but I like this. So I've got 1. Well, actually, you know what? I can go ahead and why don't I just take the square root of both sides now? Because I do know that I'm not looking for c squared. I'm just looking for c, right? So now I've got the square root of 1 squared plus 5 squared. Still with me? Okay. Okay. Taking the Algebra 1 EOC next week, and I'm super nervous and I feel unprepared. Any tips? Calm down. It's going to be fine. You're going to be great. You're going to be awesome. But if there's anything specific, put it in the chat. Okay? All right, so 1 squared plus 5. Great. So now I've got the square root of 1 squared, which is 1, plus 5 squared, which is 25. That equals c. So I'm looking at the square root of 26 equals c. Now, I'm not sure if your teacher will let you leave it like this, okay? Or if you need to actually simplify it or put it in a calculator or whatever, okay? But if you do this, okay, you go over here, don't teach it like this, just square the 1 and the 5 and add them and then square c. Yeah. So Riley, here's what I'm doing. I'm not sure when you joined, but we were talking about the distance formula, and I was saying the distance formula is just Pythagorean theorem, right? So eventually, or really in the next 30 seconds, I would then my students, I tell them to just basically start here. That's all it is, right? So if we go over to the distance formula, dun, 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 right? So the distance formula is going to be, let's fill in the distance formula and just bear with me for a second. Okay, so I've got x2 minus x1, which is, so it's 4 plus 1 squared, plus y2 minus y1, which is 2 minus 3 squared. So now I'm looking at the square root of 5 squared plus 2 minus 3 squared, which is negative 1 squared, which is the same thing as 1, right? So now I'm looking at the square root of 25 plus 1. Doesn't this look familiar? It's just Pythagorean theorem. That's all it is, right? It's just the Pythagorean theorem. So again, so when I teach this, I tell my students what the distance formula is, but I go, guys, it's just Pythagorean theorem. That's all it is, right? Once you see that, oh, yeah, that's just how much did the y change and that's how much did the x change. That's all it is, okay? So again, if you're being forced to do the distance formula, you can, right? You can do that. You can do hard things, right? But you can also check it with Pythagorean theorem. And you can ask your teacher, can I just do it with Pythagorean theorem? And they'll say, yeah. Okay? So Charles, hope that works. Okay. Let's see. Oh my gosh, got so many in the chats that I missed. Is this? Why is this not working? Okay. Linear equations. Okay, so I did linear equations. Turning circle general form to standard form. Circle equation. Trig functions like sine and cosine. Zachary Paul, limits. I may have missed your first question, but limits, if we're talking about like calc and stuff like that, we tend to do a little bit more like pre-calc is kind of my limit. My limit for like what we do on here. So, all right, Dominic, can you give me a little bit more about linear equations? What specifically you're looking for out of linear equations? Are you talking about graphing them, solving them, whatever that is? Okay, so graphing some trig functions like sine and cosine. Let's see. I have the problem in the chat. Yeah, oh, there we go. Sorry, my mouse wasn't working and I'm all the way across the room. I'm reading the chat like across the room, so sometimes it's hard for me to. Okay, oh my gosh, I missed so much in the chat. I'm sorry, guys. Let's see. There are a few problems I'm struggling with. Okay. What's the EOC? Is that is that like the Texas state? That's what happened to the TEEX and the TOS and the tax. That's what I all did. So I grew up in Texas, but I started teaching in Texas, but I don't live there or do much there anymore. But my sister still lives there. Okay, let's see. How would you do? Oh, Charles, you can do it without a grid too. It's the same idea, right? Okay. Zachary, I am not. Zero, possibly negative and undefined. Oh, positive. Oh, it's the state test for the star. Zachary Paul, the only one that I saw was the limit of h to 0 times r z plus h. That I'm not really going to get into limits and integrals and things like that. Let's see. But what does EOC stand for? Mainly graphing them after solving. Okay. So let's see. Okay, so the negative positive was that for the I don't have any calculus lectures. I am end of course. Got it. So I really only go up to like algebra 2 and pre-calc. That's kind of the limit or the scope of what I do here on this, because what I have found is, I mean, first of all, I just really like algebra stuff and trig and pre-calc and stuff like that. But what also it seems to be kind of the root of a lot of people's struggles in math starts in like algebra and geometry. And so a lot of times, even with a lot of my students that I work with in pre-calc and calculus too, a lot of it stems back to like, oh, you know what? I never really learned fractions. And it's like, okay, let's learn fractions, right? Because with fractions, you see them in complex numbers and rationalizing denominators and all blah, 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 blah. All that kind of stuff is when you see those functions and those radicals and all of that stuff, and it all gets back to the basics, right? It always goes back to the basics. It always goes back to find the pattern, recognize the pattern, work the pattern, right? I don't teach AP Calc. Oh, conic sections. I did all of that stuff. Wow. Okay, so linear functions and graphing them, or linear equations and graphing them. So when you're solving a linear equation, remember a linear equation and a linear function is just a relationship, right? And this goes for any equation, any function, anytime, no matter what, right? Even with a student that I'm working with in pre-calc right now, and we're graphing rational functions, and it's like 1 over x squared minus 2x plus 3. And we just go, you know what? We can just start plugging in values, right? It's always just a relationship, right? You know, if it's 2 to the x power, like you just start plugging in values and you'll get a good idea of what the graph is going to look like. And that's like one of the first things that you learn about graphing, right? And about graphing a line is that it's just a relationship between the two things, between the two variables. All right, so when we have a linear equation, like if we had something like y minus 3 equals 4x plus 4x minus 1. Okay, so we have something like this. So what you want to look at is you want to look at the relationship between the y and the x. Now I can graph this as it is right now, but usually it makes it a little bit easier if you can get this into a form that's a little more recognizable and a little bit easier to graph, which is the slope-intercept form. So the slope-intercept form is y equals mx plus b. This is the one that everybody usually just can rattle off. This is one you don't forget, right? It's y equals mx plus b. M is the slope. So that's going to be like the angle that it's changing. And it's really just like the change in the rise over the run. So if you think about it, it's a ramp on top of some stairs, right? It's the same idea, right? So the ramp is smoothing it out, but ultimately you're going up and forward and up and forward. Or maybe you're going down and forward and down and forward, right? So depending on the slope, and it changes, like if you have some really steep stairs, that means you're like barely going forward and you're going way down, barely forward, way down, right? Or if they're really long stairs, right? You have those like those long stairs, and then you go burp down. Then you go long stairs and then boop down, right? So the slope depends on how much you're changing vertical and horizontal, right? So thinking about a 3D printer. 3D printers just move back and forth and side to side, slightly up, right? But back and forth and side to side. But they're able to do all of those different shapes because it's just a relationship between that horizontal and vertical movement, okay? So that's what the slope really is talking about. The B always stands for y-intercept. That's where it intersects the y-axis. So we have the x-axis. This is all the x values, right? The x values, and then the y values are here. This x and this y, these make up the points, okay? So x and y, those are going to be the points. So what we want to do is to get this into slope-intercept form, I just need to get y alone and on one side. So the way I'm going to do that is we're solving these equations. So y is here, but it's y minus 3. So I just need to get rid of that 3, and I can't just take that 3 off and just not do anything else. But what I can do is to cancel this out, right, to make it so it equals 0. If I just add 3 to this side, right, I have negative 3 and I have positive 3, and those are going to cancel out. Those make those 0 pairs, right? So now I've got y by itself on this side. I can't just add 3 to this side and then move on. I've got to add 3 on this side also, right? I want to keep it in balance because otherwise I can't, it's not going to be equal to the same thing, right? Y minus 3 is 4x minus 1. So I can't just add 3 because then it wouldn't be the same thing, right? So I'm going to add 3 to both sides to keep it balanced. So you always want to try to get the y by itself in this case, right? So you always want to get the y by itself. So whatever you need to do to get that y by itself, and then x just kind of goes along for the ride, right? Everything over here just kind of ends up being whatever it is, and then we graph it, right? So y equals 4x. I haven't done anything to the 4x, right? Because those are not like terms. I can't add that 3 to 4x, but I can add the 3 to the negative 1, right? And that gives me positive 2. Okay? So if y minus 3 equals 4x minus 1, then also y equals 4x plus 2. Okay? All right. So now that I have that, I've got my information. So I know that my slope is 4. Right? And again, my slope is like, what are my steps with the stairs, right? Or with the ramp, right? So my slope is my rise over my run. Think about stairs, right? You're going up, forward, or you're going down, forward, right? So rise over run. So that means that every time I move up 4, I move forward 1. It's 4 over 1, right? Mason, yeah, you can request certain stuff if you have anything in particular about like Algebra 1, geometry. We're doing some Algebra 1 and like kind of like pre-algebra stuff right now. But if there's anything that you want to, if you need help with, then let's do it. Can you do substitution? Substitution, Slipper. Substitution in a system of equations or, Mason, you have said the magic word. I will factor polynomials any day of the week. I love factoring polynomials. Okay. Okay. Let's see. But Mason, I got a couple of other things ahead of you, and then I'll start going into those, okay? All right. So rise over run is 4 over 1, and then our y-intercept is positive 2. So that means that my line, which is y equals 4x plus 2, that means that it's going to cross the y-intercept at positive 2. I'm going to go ahead and mark that. Might as well. So positive 2 right here. Okay. And then I think about my stairs, right? I'm going, remember, to my next point, I'm going to go up 4 and over 1. So that would be up 4. Ooh, I ran out of room. But I could go backwards, right? I could go back down the stairs, right? So I'm going to go down 4 and back 1. Right? And I don't have room to do another point, but all I really need is 2 points because now I can graph this line. Okay? So even though those are my 2 points that I marked, I know that this line is going to pass through all of those little intermediate little tiny points also. Okay? So we brought down the 4x, yep, because the 4x, nothing happened to the 4x, right? So now we ended up with just the 4x plus 2. Okay, and so this graph is the line 4x plus 2 because we go up 4 and over 1. And then we would keep doing that, right? We go up 4 over 1, up 4 over 1. It's just going to keep going at that same line, that same angle the whole way. Okay, what is y in the equation? Y is the y value that's going to be on the y-axis here. X is the x value that's going to be here. So when x is -1, y is -2. Because 4 times -1 is -4, plus 2 is -2. Okay? All right. Okay. All right, so slipper number 1, again, so substitution as a 6th grader, are you doing substitution as a system of equations? That seems early to be doing as a 6th grader. Or do you mean just like with expressions and equations? We'll do some factoring polynomials, okay? So slipper, if you have some more detail, let me know. So, because we can get into substitution, but I just want to make sure we're doing the right type of substitution that you're asking for. Okay. All right. Factoring polynomials. I love it so much. Okay. Factoring polynomials. Okay. Polynomials are many-termed expressions. Okay. Many-termed expressions. Oh, Kennedy, I'm sorry. Circles. Okay. Circles. You know what, guys? You're right. Kennedy, I should do the circles first. Okay. And then we'll do polynomials. I promise, guys. I am not going to flake out on the polynomials. You know this. Okay. I just want to make sure. I haven't done circles in a long time. Okay. So the standard form of a circle. Okay. So the standard form of a circle equation. Okay. Standard form of a circle equation is x minus a squared plus y minus b squared equals r squared. Okay. And then what was the other form that you had said? I'm sorry. So there was standard form and general form? No, general form and standard form are the same thing. This is kind of the standard form of the equation. We don't need to be rude. I mean, H and K, those are the same thing as the A and B. Excuse me. There's a longer form that I need to change back into standard form. I'm wondering if those are just maybe just practice problems. like if you've got these equations, right, like so something, for example, like if you had, oh, I don't know why I erased that, but let's see. So if we have 8x plus x squared minus 2y equals 64 minus y squared. Give me something like that. Well, general form and standard form is the same thing. Stop it. So is this kind of what you're looking at? Is something like this? I'm assuming. Okay. So I'm just going to kind of go from this and see. Because Kennedy, I'm assuming that it's something like this where you need to write this into standard form. I saw that you wrote here it is, but you can't attach like questions. But is this something like that where you have to write this in standard form? Okay. I'm going to just kind of go with this. So if we think about how we want to get it back to like standard form, right? So you would have like, well, so it's going to go back to completing the square, which actually is very closely related to factoring polynomials, ladies and gentlemen. But what you want to do is you're going to get all of the x's and y's on one side, okay? Get all the x's and y's on one side, get the numbers all on the other, okay? So I'm going to not continue to use the black marker, but I'm going to add y squared here. And I'm going to rearrange all of my terms and everything so that I've got x squared plus 8x here. And then I've got y squared minus 2y here. And then I've got 64 here. Okay, so ultimately I want to get to my standard form of the equation, which is like x minus a squared plus y minus b squared equals my r squared, right? That's eventually what I want to get to. Okay. Or h and k, whatever, right? A and b, h. Oh, this squared should be outside of the parentheses. Sorry. Squared there. Okay. So eventually, I want to get back here. Okay. All right, Gojo. Thanks for joining us. See you next week. Okay. So I want to get this. So these two things are perfect squares here. Okay. So I've got the x minus a squared and y minus b squared equals r squared. Okay, so what I'm going to do is I need to complete the square. Okay, so to complete the square is a way of working with polynomials and working with quadratics and things like that, where let's look at x squared plus 8x. So I'm going to kind of look at these on their own. Not kind of, I am going to look at these on their own. Okay, I'm going to look at x squared plus 8x. Okay. To complete the square, I need to add something over here that makes it so I can make this into a perfect square binomial. The way that I do that is I'm going to look at half of this number, which is 4, right? So I take half of this, 1/2 of 8, which is 4. 4 squared is what I want to put there. So plus 16. The reason I want to do that is because then x squared plus 8x plus 16 is the same thing as the binomial x plus 4 squared. And if I FOIL this out, I would know that it's, okay, it's going to be x squared plus 4x plus 4x plus 16, which is x squared plus 8x plus 16. Okay? All right. So then I can look over at my y squared minus 2y, and I'm going to do the same thing. Y squared minus 2y. And then so I look at, okay, half of negative 2 is negative 1. Negative 1 squared is positive 1. So I'm going to have plus 1 here. So then I can rewrite this as y minus 1 squared. Okay. Whoops, that's the wrong one. Oh, maybe it is general form. No, standard. This is very confusing. It might be general form, I guess. The x squared plus y squared minus ax minus by minus c. I mean, that's basically what that is. Equals 0. Where does square root fall in the order of operation? Square root is an exponent. Okay. Let's see. So we've got these two that we would add together, right? Now, I'm running out of room. So when I do this, when I add 16 on this side, I have to add 16 on this side. When I add 1 on this side, I have to also add 1 on this side. Okay? So then, oh man, guys, you're asking really big questions and it's so late. I don't think I'm going to be able to get to all of those. But like next week, if you get here, I start between 7:30 and 8. So I can do those things, right? But like the vertical asymptotes, that's a long lesson. But I can do that next week. I can put that on my value for next week, okay? Or on my list for next week. Okay, so this would be, I've got x plus 4 squared plus y minus 1 squared equals 64 plus 16 plus 1, that is 81. And that would be my r squared, right? So my radius is 9, okay? And then my center is -4, +1. Because remember, it's the x minus a, y minus b. All right, so -4 and 1. So this is, we've got our center is here, and we've got our radius there. Okay? All right, guys, I don't think we're going to be, I don't think we're going to have any time for all right, Kennedy, good. So see you next week. I don't think we're going to have time to do our factoring polynomials, but I will absolutely do it next week. All right.
We have lots of things on the channel.
Oh my gosh, we have so many things on the channel for factoring polynomials. Like I said, it's one of my favorite things to do. I think factoring polynomials and Pythagorean theorem, my favorites. I'm going to get them tattooed on my body somewhere, sometime. That sounded weird. Sorry about that. All right, so we will do more trig next week. Systems of equations we can do next week. So just remember, I know, Mason, do you have a quiz tomorrow or something? A test tomorrow or something? Oh God, synthetic division. Yeah, we will do a ton of polynomials tomorrow. Mason, I can't remember. Did you have a quiz or something over this tomorrow? I don't want to leave you hanging with the quiz. or a test? Oh, Lopez. Let's see. Oh my God, I couldn't get this mouse to work for a while, and I was like, ah! Okay. All right. So, guys, next week, we will do factoring polynomials, dividing polynomials. I know the polynomials, they're my favorite. And we'll do systems of equations next week, okay? So, make sure you guys, click, like, subscribe, all that stuff. I really enjoy the process of factoring polynomials too. Mason, I will put it top of my list next week. So join in right at 8 o'clock. So guys, I know it's getting into be time for finals and all of that. So make sure that Lucas, there you go. So make sure you join next week on Thursday for Mathursday. And if you have any questions, if you need any tutoring or anything like that, if you have any questions, please, please, please send me a message, ask me a question, and you can do hard things. You can do math. All right. Have a good night, guys.
You have to end it.
Oh, I do have to end it. Nick, no. I can't do that at the very end. All right, guys. Adios.